All right, well, this week I am extremely excited to be here with Bob Parks, who was the originally co-founder and now the CEO of Optical Perspectives Group. Bob has an extremely extensive history in optics. Before we started, I should have made sure it's okay to call you Bob and not Robert, but too late for that. So before we get into it, of the people that know you, and I think a lot of people in Tucson who came from the College of Optics are aware of who you are, your name's kind of, amongst those names of like Gaskell and these names of the people who really set the foundation for a lot of the optics we use. But you and the point spread microscope, like when I think of Bob Parks, I think point spread microscope, and that opens up a lot of avenues. So that's really going to be kind of the topic today. And before we get there, I mean, how did you get into optics?
Well, first of all, let me say, Logan, it's just a pleasure to be here.
Yeah, likewise. For you and me both. I'm really excited for this one. So
good. So how did I get into optics? Just as in the news today, it was the Russians. Back, I was in high school in the Cold War era and sort of thought I'd go to college and major in English or history because my parents had done sort of the same thing. And then the Russians set off Sputnik, and it no longer seemed, or there seemed to be a reason, since I could do math and science stuff, that maybe this was a better choice for college. On the other hand, I still liked the humanities and literature and that sort of stuff, so I went to a liberal arts college and majored in physics.
Okay.
After that, kind of keeping in the science and liberal arts theme, I thought, well, I could get a master's in history of science. Now, when I went off to Williams College for their very small master's program, they said, well, the guy you'd like to be with for an advisor is going to retire in a year. We've got you hooked up with Dr. Brown. So I went to see him, and he said, well, it's nice you're interested in history of science, but I'm doing laser work. He said, do you think you can use an AutoCollimator to line up end mirrors on a laser cavity? And I said, yeah, I think so. He said, wonderful. Show up at 9 o'clock tomorrow morning and we'll get busy. And so that's how we got into it, doing an experiment that I had nothing to do with. He had the idea, raised the money, got the equipment, but end up writing a paper that people are still contemporaneously referring to about second harmonic generation of light off of a thin metal film. It's a plasmon effect. So as I say, I didn't do anything but kind of turn the crank, but that's how I got into optics.
And you say you didn't do anything, but I think that describes a lot of graduate work anyways, is you come into a program and your advisor says, this is what you're working on, right?
Yeah, and you have essentially no control.
Right, and you say, sounds great. It's interesting that you say that when you got there, you used the phrase that you said, oh, how do you feel about using an autocollimator? Was your undergraduate work pretty intensive with respect to kind of like the hardware side of things?
I would say yes. I had an extremely good, I thought, physics teacher named Thomas Dillman. He was actually a nuclear scientist, but he ran this fairly sophisticated lab that we got to do. We were supposed to be redoing Millikan oil drop or something like that. And we got to use a lot of very nice equipment, and we had to write up a report, and it had to be in his hands by 8 a.m. Monday morning. And it was tough to do sometimes. But no, it was a tremendous background. He was at Wesleyan, and it was a great physics program.
I realized as well, I forget to click that button. There we go. It's interesting to me because I've spoken to a lot of people. I'm deviating already, so I apologize, but I'll get us back on track to the PSM. But I've spoken to a lot of people who have gone through undergraduate engineering programs of all sorts, optics, biomedical, or basically any genre. And the consensus oftentimes is you learn a lot of superficial things, but you don't necessarily learn to a depth where if somebody put you on the spot and said, you're ready to come in and use an auto-collimator on whatever, I think a lot of people that I've spoken to anyways out of their undergrad would have kind of blanched and said like, well, I don't know, or maybe I can use it.
Well, I think though too, having a physics degree as opposed to an engineering degree, physics is kind of a foundation where you can go off and do many, many different things and,
right.
and feel comfortable. And where if you go to school and specialize, you've kind of tied your hands behind your back.
Yeah.
I just think physics is a great place to start.
Right.
And then
you can always dive into whatever.
You.
Yeah,
right.
Absolutely. So that takes us through how you got into optics and your master's program and generating second harmonics, which is fascinating. That sounds like plasma work. How did you go from that into the point spread microscope? And I'm skipping ahead because, I mean, how'd you go from that into auto-stigmatic microscopes?
Right. Well, this second harmonic generation leads you into like quantum optics and that sort of thing. And I just say, well, I'll go get a PhD and go to Rochester and work for Emil Wolf, and I forget his colleague's name that was doing the same sorts of things. And so I got a nice NSF fellowship. But what I didn't realize, and I'm just plain naive, was how seriously the University of Rochester physics department took their physics, and particularly it's essentially a nuclear physics department.
Really?
Yeah. And so after the first semester, I withdrew because I knew they were going to kick me out at the end of the second. The most notable thing about that's where I met Jim Wyant in the math physics class there. I mean, we weren't friends or anything, but we were aware of each other's presence. And we both agreed that, I don't know what the woman's name was, but the smartest person in that math physics class was a woman who brought her baby to class in a basket.
Wow.
Yeah.
Jeez, talk about dedication yeah.
So I withdrew from U of R, and my wife, who already worked at Kodak, said, Bob, the draft board's going to get you. You're already 1A. I said, yeah, but I'm going to go apply, see if I can work at Kodak. She says, well, they don't hire people off the street. So I went and applied anyway, and the fact that I had some optics background, I was immediately hired.
Right.
And from there, they were doing some proprietary work, and so you had to get a certain level of clearance before they got you into the real job you wanted. And per the PSM question, the job was measuring the radius of curvature of long radius test plates. And what you're using is an auto-stigmatic microscope. It's an AutoCollimator with an objective on it.
All right.
And so I didn't realize at the time that's what I was using, but I could see it was doing the job it was supposed to do and did it well. And then went on to iTech from Kodak and used essentially the detector end of Point Source Microscope. It was a microscope looking at the image of some cameras, and we used a quad cell to see whether the image was centered. Mm-hmm. And we were measuring distortion. And the only reason for not doing it visible was one of the cameras was an IR camera, so you couldn't see the light. So to make all the cameras over the spectral range match, we use the quad cell for all of them.
And can you, because I think even a lot of people in optics may not be familiar, but can you just describe what a quad cell is, kind of what the key operating principle is for it?
Oh, the microscope or the PSM?
The quad cell specifically.
Oh, the quad cell, yeah. It's just a silicon detector divided into 4 quadrants. And so if the light falls on one of the quadrants, you know you're decentered.
You can see where you're off.
And
right.
You want the spot to be equally illuminating all 4
right.
quadrants where they meet, like 4
right,
corners
right.
here, the state. So we did that, and that worked out well. And then I went to Frank Cook, who was ran an optics shop that specialized in prototype and hard-to-do optics. And one of the things they were making were hyperhemispherical domes, where the spec on the drawing said the centers of curvature of the 2 surfaces had to be within some couple thousandths of an inch.
Right.
And the guy who was sort of the metrology chief, guy named Ray Boyd, had worked at American Optical, where early work in fiber optics was done. And he could get fiber preforms, and he would draw them down to a very sharp point. You could put a microscope illuminator light at the bigger end of the fiber, and you got a point source.
Point source, right.
And he used cork and an eyepiece and jammed it all together, and had something where you could look at the center of curvature of this dome, and in 3 dimensions you had how concentric they were, and so that was neat.
Right.
Again,
right.
another little bit that fits in the piece.
I want to stop people because I want to stop here just briefly because I think a lot of people, especially people that don't necessarily work in metrology, don't understand how much metrology. I've been in scenarios like that where you're saying, how do we measure this? Right? Like you have some problem of like, hey guys, we need to measure this thing. We need to measure the concentricity of these, pseudo-meniscus type shape. And sometimes you have to think like, what are we going to do? And you have to come up with a new approach. That's a fun area of optics for me because a lot of other areas, kind of like you said, it's engineering as opposed to, I guess this is engineering, but it's very innovative engineering to take this brand new approach and apply it to it. So, I just wanted to call that out because I think it's such a fascinating thing about optics and metrology.
Well, you do have to think a little bit out of the box. You really have so many tools available in optics, but you don't always use them the way they were originally designed to be used.
Right.
But they still work.
Yeah.
Light goes right or left as far as well as right, and so you may have to think of things backwards.
And even making the leap from they're 2 spheres, they have centers of curvature. If I pull on this fiber and illuminate it, it's pretty much a point. And I know making these leaps from the theory to a practical application is just a fun thing.
Well, the other thing in optics, we were talking a little bit about how important optics is in general to metrology and just everyday life. If you tried to measure the concentricity of those 2 mechanically with gauges, that's tough. It will take you a lot of equipment and a lot of time to get the answer you want, where if you do it optically, it takes you practically no time with pretty trivial equipment.
And you don't have to touch it. You don't have to there's not no risk, but low risk of damaging the surface. It's a lot of benefit. So, But I interrupted you. So you came up you guys came up with this approach, and it sounds like the beginnings of the point spread microscope.
Right, and then because I knew some optical background, when the opportunity to run the shop here at Optical Sciences, or the College of Optical Sciences, I just jumped on the job because, or to get interviewed or whatever. Because when I worked at Kodak, Aidan Meinl, who had started Optical Sciences, the people at Kodak thought he walked on water. And so when there was the opportunity to actually work there, I don't think I even asked my wife. I just said, we're moving.
And Meinl was there at the time?
Yes.
Okay.
Peter Franken, who again, another total coincidence, was a founder of Second Harmonic Light Generation, was director at the time, and he was the one that hired me. And he said, Bob, you can do anything you want as long as you don't bring embarrassment on the center or anything, down to the shop that you want. And so it gave me great freedom to do a lot of very interesting things. And the opticians would listen to me because I actually, from my experience with Frank Cook, knew how to polish and run a generator and all that. I mean, I had the math background, but also
practical,
I could talk their jargon.
And
I knew what was going to happen with getting scratches on surfaces and whatnot. So then we needed to make some optics where this thing I'd learned about at Frank Cook's would have come in useful, and we found an eyepiece, fiber optic eyepiece, that EG&G made that already had the fiber right in the eyepiece. And so we just buy it commercially, put it on the end of a microscope, and we had a way of feeding the light into the fiber or into the microscope, and then seeing in the eyepiece where the reflected light was. And that worked beautifully. And we thought we're all done until we tried to order another one day, and they said, sorry, we no longer make these. The guy that used to make them is retired, and that's it.
Right. That's all you have to work with.
So then, about that time, I wound down at the shop and started consulting, and we got a job where people needed to put, for a laser scanner lens, all these centers of curvature of lenses, concave spheres, toroidal lenses, all just in a straight line. And just looked like a perfect place for that thing. I mean, the call came to it. A guy wanted to know where he could get a big stage that he could put his lens bench on and be able to move it and do it accurately. And I said, I don't think well on my feet. Let me call you back in 15 minutes. And I thought about this and thinking of Newport or Aerotech and how much it was going to cost to put mounts together that were going to hold this 80-pound thing. And I thought, I said, but a Bridport milling machine, it's a great XYZ stage, right?
Right.
We'll put the
great
microscope
precision
in the chuck and put the lens bench on the table, and off we go. And so this was, and then we had to really build an electronic, and this is where I did this with Bill Kuhn at the very beginnings of optical perspectives, and we got a patent on this device. I mean, first of all, it took this company from an assembly thing that took them 2 weeks to something that could be done in 4 hours. And many years later, the technician who was using this then to put their assemblies together, I met him at an entrance to the old Zygo facility here. He recognized me, and he literally came up and hugged me. He said, "You don't know how much easier you made my life with that instrument."
Wow.
Yeah, and I thought, well, there must be value here.
That's about as good a feedback as you can get.
Well, our very first PSM, we used a Shack Q, which I'd learned about at Optical Sciences, and the spherical reference surface served as our reference, and then the light reflecting back. And Shack himself, realized you could use it this
Right,
way, but
right.
using it as an interferometer made more sense. But you can also use it for an alignment, just like you can use an interferometer for alignment.
Right, right.
And it was early on in lasers and cameras and all, so we had an analog camera behind the Shack Cube, but then realized that once you get one reflected spot behind the other, you can't do any better than that. And that was, you could get them to a couple thousandths of an inch, maybe a little better. And that's where Bill Kuhn realized that using LabVIEW and digital cameras, you could put an electronic crosshair on the CCD array.
Right.
And all you had then was the one spot coming back, and you could centrate on that to a 10,000th of an inch or better. And so we gotten a patent on the first one, but we were out of money by that time and couldn't patent the second one. But it did what it was supposed to do, and that's kind of, we've gone from there using essentially the same design, same hardware.
Right.
I mean, we keep making small improvements.
Right, right.
But, and mostly in software, but that's where it came from.
And I'll link to the paper and your websites. You've published, I think, over 100 papers, and several of them are on the PSM, how, what the components are and things of that nature. But a lot of things were upgraded. So in my mind, you went from, on the detector side of things, you're saying in your days at Kodak, or even before, you're using a quad cell. You're now using a digital detector. It has a digital crosshair on it, and you can know really precisely, okay, you're centered or you're not centered, and this is where you need to go.
Well, it's two. We couldn't have built it in the Kodak days.
Right.
Because the technology wasn't there. We didn't have the computers, we didn't have the digital camera, we didn't have lasers.
Right, right.
And one of the things Jim Wyatt and I love to talk about is whether interferometry or slope measuring tests would be what everybody does these days.
Without the
depending on, whether computer technology or laser came first.
Oh, wow.
And opticians were familiar with fringe patterns from test plate matches, and so when you could do that with a long coherence laser, that seemed like the way to do it, because computers weren't up to yet integrating slope data to give you surface maps, and the optician needed to know where the eye places were.
Right. Huh. Yeah, that's interesting.
But I think if computers had been just a little more advanced than the laser technology, we'd all be using wavefront sensors instead of interferometers.
Right. Yeah, and that goes towards my research was on deflectometry and slope measurements. But so once you had kind of firmly, I would call it invented, and you had the patent on the first version, not on the second one, but of the PSM, you're still working in the optical fab shop. I don't know the technical name.
I'd left optical sciences.
At this point you were
fully on my own.
Okay, and you guys, and this was a consulting company. This is Optical Perspectives.
Right.
Okay. So what did you do then? I mean, in my mind, you're sitting on. You realize this is an incredible device for all sorts of applications. Did people immediately start picking it up and saying,
"No,
this is the best thing since sliced bread"? Or yeah. So what happened?
Well, no, things got off the ground really very slowly. One, though, of our first customers was Raytech here in town, because this company where the technician came up to hug me, a fella named Pat McCarthy was one of the engineers there, but the company folded up and Pat went to work for Raytech. So he was kind of an inside salesperson. He knew what the PSM would do and said, "Hey, you guys at Raytech, this could really help you out.
Right.
Some of your alignment issues." And so, Raytheon's been a good customer. The people that, I mean, most people's eyes glaze over when you first tell them, because first you got to know what an AutoCollimator does, then what it's going to do with the objective on it. And people just don't get it. But the people who do are astronomy students.
Yep.
Particularly the ones that run the instruments. Because, if you've got time on the telescope, things have to work.
Right. Right.
And they know how to make and understand.
Yeah, things of that nature.
Yeah.
I want to get to several of the papers you sent me, and they all were audio so. And yes, so what I wanted to jump into is we're going to talk about Axicons as well, but I kind of took it for granted. Can you explain an auto-collimator? Because you're right, that is a core principle when we're even talking about auto-stigmatic microscopes with PSM.
Right. Well, an auto-collimator is a telescope that's got a beam splitter right in front of the eyepiece, and so that you can put a light source or crosshair at the point where when it's re-imaged, it'll be on the crosshair in the eyepiece. And so you're sending out a collimated beam reflected off a plane mirror, comes back refocused, and you'll see the crosshair,
right,
illuminated crosshair, overlaid on top of the crosshair in the eyepiece.
Mm-hmm. And you can use that commonly for alignment purposes.
Yes.
Right? I wish I had you around several years ago, because I was in a job interview and they deviated rapidly from questions about some of my research to explain an auto-collimator. I was caught flat-footed. My explanation was not satisfactory. Okay, so it's a very common device, very common especially for use in aligning things. And again, I kind of let this get away from me, but I will let you answer. Why is aligning things so important, especially in optics? Why does it matter? Why go to any of this work?
This
right?
is my favorite question. Well, you've got lens design programs now that can design, as far as the field goes or whatever, essentially perfect. For the specifications, you can't do any better than what the computer's going to tell you.
It's perfect. It's perfect, right.
And with things like this magneto-rheological polishing or ion beam polishing, you can make essentially perfect optics. So the only place you can get better performance now out of an optical system is to put it together better.
Right.
And that's why alignment's important, because it's the last thing that we've got out there to work on to get better performance.
Yeah, I think that's a beautiful way to put it. And I usually put it in a more cynical take, in the sense of, you've designed something perfect on your computer, but it doesn't mean anything until you actually have it put together. And we touched on this basically because it's a favorite point of mine with all of the recent guests, that lenses get tipped and tilted and decentered and shifted and all sorts of things. So alignment clearly has to have been a large part of, I would imagine, all of your work throughout your career. Is that accurate, or?
Yeah, and it's because, and particularly work at the university, we'd get people that want a parabola or an off-axis parabola or something like this. Well, you got to test the things to show that they're good enough that you can actually ship it. And you can't test it unless it's aligned.
Right.
So, yeah, alignment is fundamental to just doing the test to get the stuff out of the shop.
To actually say you built it and you built it right.
Yeah.
And I wonder if now's a good time to get into it, but at some point, you had alluded to this, that you also were called in. Was this after Optical Perspectives that you served as well on the board investigating the Hubble?
Oh, yeah.
Is that
Well,
nearing time to, this point where you said, okay, we've gotten the patent on the PSM, and you're saying, what are we going to do with the PSM? Was that near in this time, or is it a little further off?
No, it was in that time. As I said, PSM wasn't selling.
Right.
Like-
You had your inside sales guy at Raytheon.
Right. And we would sell, I don't know, for a year, maybe, if we were lucky, 6 a year,
Right.
maybe. So I needed other sources of income, so I kept consulting. And when the Hubble error was discovered, NASA had backup plans in case this happened, and they had planned to bring together a committee of people, and General Lou Allen, who was director at JPL, was head of the board, and he had 6 people, experts, that were supposed to come to a conclusion on this. And from the university, Bob Shannon was one of them. Roger Angel was another.
Huh.
And the third person I knew on the committee was Chuck Spoolhoff, who'd been my boss's boss at Kodak.
Oh, wow.
And I knew, I think, one of the NASA people somehow. But anyway, when they had their first meeting, they realized they were going to need somebody just to kind of turn the crank and get them the information they needed. And Bob Shannon suggested my name to the committee, and I was hired to do this and spend time at Hughes Danbury to, the committee would say, we need to know this, we need to know that, and it was my job to get the information for them. And we were working hard to get all this stuff, and it was maybe the third meeting. General Allen said, this can't go on forever, we got to write a report. I want you to take this chapter, Bob Shannon, about the design. I want you, NASA guy, to talk about quality assurance. And when he was all done, he wheeled around in his chair and looked at me, who was kind of in the audience because I wasn't really on the board, and said, Bob, why don't you do the chapter on the mechanism by which the fault happened? Well, we'd been working hard, but we had no idea at that time. And I thought, oh my God. And because they had this beautiful procedure for how to do the test, and if you followed the procedure, you couldn't possibly make the mistake in testing the mirror that was made. And it finally, just by partly process of elimination, we realized that they hadn't followed the procedure.
Huh.
And then it was a matter of finding out why they hadn't followed the procedure. And one of the QA people who had worked during the time of the program and then came back later during the investigation kind of gave the clue to this. I'd put up pictures on the bulletin board of different aspects of the thing. And he said, Bob, I think you ought to look harder at that cap on the measuring rod. And it was still up in the test tower there. We got it down. We measured measuring rods too. I mean, one of the things that was kind of scary in all this was one of the measuring rods had this clamp in the center of it, but we didn't know what or why.
Why it's
and
there.
It was X-rayed, and the gap in the center of the thing was just about
Unbelievable.
the distance of the error. On the other hand, the rod measured the right length. And I think what happened is whoever made it in the first place made it a little bit too short. It was tough to get more invar quickly, and somebody said, well, just cut it in two, we'll space it out and try again. But the problem was this long thing wouldn't actually fit in the null lens the way they planned to. There was an opening in the side, it was supposed to go in, it didn't fit. They couldn't use the measuring rod.
Did it not fit because should it have fit?
Well, yes and no.
Okay.
they'd use the same null lens to work on a practice mirror to convince NASA they knew what they were doing.
Right.
But then the real mirror was slightly different. I think it was bigger diameter, and they had to extend this field lens that was misspaced, extend it in this snout, and use a longer rod. And the hole they'd cut originally in the side of the lens to get the rod in, no one had ever thought,
Yep.
will the new rod go in and fit down the snout?
Right.
And the answer was no.
This is the reason I asked that is Jim Burge and Matt Dubin both hammered it into my head that before you put things together, you better be sure you can test them in whatever way you're going to test them. But anyways.
Yeah. Well, at Frank Cook's, he talked about just making cardboard templates of big pieces of glass to make sure when you put them on the blanchard, they didn't hit the guards. Or, do the simplest thing possible to see that on a first order basis, things work.
Right. Because for people that haven't put optics together, once you get everything in there, it sure is hard to try to tease it apart, to say, oops, I need to test or realign some lens in the middle of these things. How can I get there?
Or a lens gets jammed in a cell, putting it initially. Yep. It's tough to get back out.
Right. And it tends to be the case that we end up making correctors for the system as opposed to trying to readjust the system, to allude to how hard it is. So at this point in my mind, I mean, you obviously have a prestigious career. You're part of, the Hubble committee. You're doing consulting, and you're selling 4 to 6 PSMs per year. And that's the part that's just mind blowing to me, because once you use a PSM, to me, anyways, it was like, this is it. Like, this is it. This is what you need. And I just can't get over the 4 to 6 thing. So do sales pick up at any point, or?
Well, the PSM sells itself to people who understand what it'll do.
Right.
There are very few people that actually understand what it'll do. And so selling is strictly a matter of educating people. Mm-hmm. And what I love about it is people will come up at a trade show and say, will it do so-and-so? And I'll have to say, I never thought of that. Let's see.
Yeah, we'll find out.
I mean, one of them was these SMRs that they use with a laser tracker.
Yep.
It's a corner cube in a sphere. And you want the apex of the corner cube to be at the center of the sphere. And a guy came up and asked if it would do that. Well, I knew about testing corner cubes with an interferometer and stuff like that, but I'd never thought about what happens when you actually focus at the apex. Well, the first place the apex is damaged, or you can't have a perfect focus at the apex, so you've got to move aside. But the reflection is just as though you would focus at the center of a spherical ball. Mm-hmm. It behaves exactly the same way. And so now if you've got the ball that the corner cube's in a kinematic mount, and tip it, and if that spot moves, you know that the apex of the corner cube isn't.
Right.
And you can calculate how far it's misaligned.
And so this is going to get into the topic of education about the PSM and its uses. And
well, on your question there, too, in terms of people who know about it, students in optical sciences are my best inside salespeople.
Yep.
Because when they go to Lincoln Labs or Raytech or who's the latest, FLIR or whomever, they get in there and they say, oh, you're doing this? Why don't you use a PSM?
Yeah.
It'll take you no time at all.
It's funny.
Or NASA Goddard is another big user.
It's funny you say that. I had a friend who went to MIT Lincoln Labs, and that was exactly what he said. He said, I think a PSM would be really good for this project. So I'll have to tell him you said that. But that's where I learned about the PSM, was in I think in Jim Burge's optomechanical lab course, and you mentioned the idea of using this to measure an SMR. When I think about the PSM, a lot of it, this is predicated on the lab, was based around steel balls. I'm going to use reflective balls of some nature. How does that tie into alignment? So when people, right, like again, for people that don't do assembly or alignment, okay, I get that I can use a PSM to focus on the surface of an optic, because if I'm focusing on the surface, the light's going to hit, come back normal, got it. How does it help me aligning the optic besides just knowing I'm at the surface? I think this is where
well, that's the perfect question, because
finally,
the PSM does nothing more than take a center of curvature of something that you can't touch, you can't feel, it's just floating in air somewhere. I mean, it's a little bit like, and it's like your lenses on the computer. They're floating on the screen, right?
Right.
But in real world, there's gravity.
Yeah.
And things sit in metal frames. They're touchable things. And the PSM is nothing more than something that lets you go from this thing you can't touch to, say, it's center of a ball, which you can touch.
Right.
And now it ties the very important optical datums to mechanical datums.
Right.
So that you know how to push things around to get them where you want them.
Right.
I mean, that's all it's a transfer device.
Yeah.
It's a little bit like a height gauge. You do it with your indicator, and then you go over to the height gauge, and it tells you how high your indicator was. Well, that's all the PSM's doing.
Yeah.
It's taking something you can't touch and allowing you to put it in a form that you can touch and that mechanical engineers are familiar with.
Right. You're sure that you didn't want to study philosophy of science instead of history of science, because
Well,
you have a great way of translating these complex subjects into something that's understandable. But okay, so that presents the very high level picture of the idea that it's a transfer function. It's taking something that's virtual or not real. Here's my focal point. It's a thing in space that's predicated on where everything else is, and it translates it to the reality of, oh, by the way, things are mounted, and I can touch them and interact with them. So if you don't mind, I mean, just going through a few basic scenarios, I think that would be great to let people get their minds wrapped around, okay, I got it. Here's how I use the PSM. And for us, the first thing that we learned was even the most basic thing. How do I verify the focal length of a reflecting optic, or not even a reflecting optic, but we'll say a reflecting optic. What we did in the lab was, okay, we have the PSM, and I'm skipping a key thing because I want to get to it with your CGH paper, but I have my PSM, I have my, let's call it concave optic, and first of all, I'll focus on the surface of the optic, right? And then I can back up, and at a certain point, the focal point from the PSM is going to be at the center of curvature of my surface. And at that point, it should come straight back into the PSM. And that lateral distance lets me say, okay, I know now the focal length, center of curvature distance, and the focal length, right? So that's a very basic use. How do I go from there to actually aligning the optic? So how do I go from, okay, well, I know the distance, but that doesn't tell me, let's say it's mounted let's say it's just that optic, and it's mounted in some fixture. That doesn't tell me anything about, is it tilted, is it decentered? So how do I get that information?
Well, if it's a, say, concave mirror, then presumably, and it's going to go in a cell, you presumably want its center of curvature centered in the cell. And so you've can put a ball at the center of the cell, mechanically measure that it's at the center. Then you take the ball away. Then you look at the ball with the PSM or an auto-stigmatic microscope, so that it's focused at the center of the ball. You're using the ball as though it's a convex mirror.
Right.
Then you take the ball away and you're looking at your mirror, and you want the light reflected from the mirror to, again, be centered on the crosshairs of the PSM, so you tilt it or translate it until it is.
And I think there's one component of using this PSM that we may have not covered. In all of these scenarios, how am I holding the PSM?
Oh, just on an XYZ stage.
Okay, and it's a fixed. The reason I ask this is in the labs we use the coordinate measuring machine a lot of the times, and again, for people that don't do alignment or assembly, it's a fancy XYZ stage.
Yes.
Right. Okay.
That's it, and it takes, people say, well, I paid $50,000 for the CMM, and you're calling it an XYZ stage.
It's a really fancy XYZ stage.
But yeah, it covers huge distances, and if you tried to put an XYZ stage together any other way, it'd be tough.
Right.
But the CMM, the beauty there is you can mount the PSM in instead of the touch probe in the RAM. You go over to the master ball, zero it out, then you come over to your assembly, and with the PSM pick up mechanical datum points on the assembly, so you know where the cell or assembly is, and then a combination of your optical and mechanical drawings tells you where every center of curvature in that ought to be. And once you picked up the datums, you're in the coordinate system of the drawing now, relative to the software and the CMM. So you just have to move the CMM to these places and that's what we did on this very early job. And sometimes the centers of curvature, because there's lenses in between, aren't the actual center of curvature, but they're where the center of curvature appears to be after it's been refracted through these optics. The other thing is, people say, I can't see the whole aperture. You don't need to, because alignment is paraxial.
And okay, you're going to have to explain that one, because it's not intuitive at all. Or it is intuitive, and then, at least in my case, you convince yourself after learning about aberration theory, it must be more complicated. And then you go back to, no, it is paraxial, so.
Well, if you've got a quarter wave sphere, all right, but it's fast F number, right?
Right.
But do you believe if you look at this little portion of it, it's any less quarter wave than this portion?
Right.
I mean, if you've looked a little bit, you kind of know what the whole thing looks like.
Right, in terms of rigid body alignment, and not this is clearly a different subject, but not surface figure area.
Yeah, if you're not looking for aberrations. On the other hand, PSM is a great star tester. If you've clamped your mirror too tightly, you'll see that what should have been a spot, you'll see spikes on it.
Right.
You know instantly that something's not right.
Yeah, because you're sending that, an approximation of that ideal point, and it's going through your transfer function, your lens or optic, whatever the case may be. And if you don't get something back that you expect, that diffracted image, then something's wrong. So before we get to the papers, how do you, and maybe actually this is the right time to bring up papers. So the first thing is, okay, I'm going to align some system, whether it be just a single lens in a module or maybe multiple lenses in a full assembly or subassembly. And we've stated the PSM's on an XY stage, and maybe it's on a really fancy XY stage, but nonetheless, that's what it is. What happens if my XY stage is, how do I know how accurate it is? Maybe I paid $50,000 and they tell me it's good to 1 nanometer XYZ. How do I know? And you sent a paper about this, which is really what I want to talk about.
Well, this is where the Bezel beams come in. And which is a total irony for me because very early in my career I said, oh, this is just a physicist,
Right.
something that has no practical value. Well,
Right.
they proved it does for many things, but as near as I know, I'm the only one doing
Right.
alignment with Bezel beams because the Bezel beam acts like a single ray in a ray trace program. And so if you've got, well, so since it's like a single ray, it's like a laser beam except up to 100 times smaller in diameter than a laser beam, or at least the central core of it is. And so if I've got a stage and I've got my Bezel beam coming here and I'm looking at it with a PSM and I crank the stage back, I can see every little jiggle in the stage because that Bezel beam will move around.
Right. Right.
And I can tell straightness of a stage to 1/10 of a micron with a 10x objective on the PSM.
Right.
But the other thing you do then, if you project a Bezel beam through a lens, say the lens isn't there to begin with, but you've got the PSM one way or another. Here you're looking at your Bezel beam, it's centered. Now you stick your lens in the beam. Well, that lens has to be, there are multiple solutions if you're up close to the lens, but if you get a long way away, that lens has to be good in tilt and decenter
Yep.
for the light to ever get there.
Right.
And what's fascinating now is it's got something to do with Hamiltonian optics and iconals, which I essentially know nothing about, except they can be used, I think, to prove how well you can do, or how many rays you need to perfectly align something, and how they need to be spaced.
Huh. And how do you make a Bezel beam?
Well, this, again, is a bit of an irony. When I was at Kodak, an emeritus employee named John McLeod was there and told us things about kinematics, but it's John McLeod invented the Axicon.
Really?
Yeah.
Wow.
And in his second paper, which I believe was published in 1960, he said this thing works great for creating beams which you can align things with. He didn't call them Bezel beams because I don't think he knew what they were.
Right. Right.
He just knew he had a beam that he could align things with. And he said this would really work even better if I had a brighter light source. And this was the year the helium neon laser was invented.
Wow.
So the traditional, well then it was like 1984 or 86 or something when Durnan and all at University of Rochester first published their paper about Bezel beams. Mm-hmm. And they made them by shining a collimated beam onto a circular aperture. And you need a lens in there too, but then that puts the light and makes a beam that you can describe with a Bezel function. It's very light inefficient because you're only using this narrow band, but it produces a Bezel beam.
It works nonetheless. Yeah.
Very shortly after that, I believe they were Finnish people said, oh yeah, but you can do the same thing with a grating. A grating of equally spaced concentric circles produced exactly the same thing. And with McLeod, you can do it with this cone-shaped lens.
Right.
All create Bezel beams. Most people assume you illuminate your grating or Axicon with a collimated wavefront. And if you do, this gives you a finite extent of your Bezel beam.
Yep.
If you illuminate it with a point source, the beam, if your grating's big enough, and it doesn't have to be very big,
Right.
will go to infinity.
Huh.
You have, now it gets dimmer and dimmer, but
you have fall off.
Essentially the beam goes on forever. I've measured 30 feet.
Huh.
You can still see it.
Wow.
And yet it behaves like a single ray and ray trace program. And if you have a lens and you focus down so that the objective is focused at the principal plane, you can move all the way across that lens and the spot doesn't move.
Mm-hmm.
You get a little bit above or below, the spot moves this way or this way.
Right.
But you can focus on, or measure where the principal plane is to a micron or two.
Again, these fully virtual, non-physically real things that
Right. But then you can back the microscope up to the surface and get a cat's eye reflection here and know exactly how far the principal plane is from that surface.
Huh. And so you mentioned it with the Finnish group suggested, look, if we print concentric rings on something, then we can generate a bezel beam. That's what you use in this paper, and you refer to it that if you can print this pattern onto a hologram, or I'm just going to call it computer-generated holograms from here on out, I'll use it, then first of all, it's roughly flat, right?
Yes, it's perfect. Well, they use photomass substrate, so
right.
It's
yeah,
really flat.
I should not say roughly. It's flat for all intents and purposes. It's flat.
And they write it with E-beam, so the circles are as
perfect.
good as you can make.
Everything's perfect. Again, for all intents and purposes. Why is that important? Why is it important that I get the pattern being perfect makes sense. I want to have a good ideal bezel beam. Why does it being flat matter?
Well, you now have a flat, which gives you 2 degrees of freedom, but it's got an axis. So your flat defines 4 degrees of freedom.
Yeah, that just blew me away when I was reading the paper. That blew me away.
Yeah. I mean, in one sense, it defines 5 since it's physically
located,
you know
right?
Where it
right.
is.
So the only one not defined is going to be rotation about the center. Why is this important? I'm getting jazzed about this, and I'm saying, oh my goodness, you have 5 degrees of freedom defined. It's a flat with a perfect bezel beam generator, and I know that I can use this with a PSM, but why? What does this give me that everything else we described doesn't?
Well, for one, you can put a lens on a stage up above, and I'm just doing it this way because that's the way my hardware is configured. With a lens up above your grating, you get light coming in from below, and move the lens through the beam, and you get a finite distance above, and you can track where the light's coming through. Mm-hmm. You can go to a second plane, track again. So now you know the position and angle of rays coming through the lens as you scan across the aperture. Well, who needs to do that for a plano convex lens, right?
Right.
But your cell phone's got these weirdo A-spheres in it.
Right.
And they typically are measured with a Panasonic something or other machine that damages the lens and takes a reasonably finite amount of time, and you got to measure both sides. Mm-hmm. This allows you to do an optical test in 2 ways. I mean, it's a slope measuring test, granted.
Right.
But you tell in transmission, is this lens per prescription or not?
Right.
And do it in a fraction of the time that you can do it mechanically.
And
that's the other point about optics. Everything's serial. I mean, everything's parallel as opposed to doing mechanical measurements. Mechanical, you do 1 point at a time.
Right.
Optics, you've got 1 million pixels in your camera, right? You're doing everything parallel processing.
Right.
So that the process is fundamentally almost infinitely more
higher throughput or faster. Yes. And that was a big thing. That was a big thing in some of our deflectometry work, was to suggest we can measure these things a lot faster than if we're physically trying to touch it, especially when we're measuring very rough infrared measurements of the grinding phase of a telescope mirror. Is the usage of bezel beams with the PSM only practical in transmission?
No.
Is a leading question, so sorry, I should have just skipped ahead and said, tell me how it's useful in reflection.
Well, it's interesting. You got to build some more complicated hardware in that you've got to get the Bezel beam in front of the microscope or PSM. Right. But I mean, that's the other thing that isn't obvious. Using the Bezel beam in all your classical optics, you think of things coming to focus and into conjugates. Bezel beams just keep going.
Right, right.
And in fact, this has come back to the Hamiltonian business. The ray you trace with Hamiltonians, you don't want it to go through a conjugate point.
Right.
You specifically don't want it to do that. And this is why I think for alignment, if you can use the Hamiltonians, you can say, okay, if I put a ray into a lens at this angle at this point, the lens has to be centered if it comes out at this point.
Right.
And you've done it with one ray.
Yeah.
You know everything you've got to know the lens design of the lens, but one ray. The other thing, beauty, and we got back to the photomask and stuff. If you put two Bezel beams on a photomask, a specific distance apart, you've now defined two rays a specific distance apart that are exactly parallel to each other. So if you're trying to line up a stereo zoom microscope or something like that, it's the perfect template to use for alignment.
And this gets into this riffs nicely off of the fact that I spoke with Shelby over at AOM, Arizona Optical Metrology, and so this helps to give application to the CGHs that they fabricate.
And they're the ones that were making.
Sure, right. And there's two last things I guess I want to cover before I shift a little bit to the final questions. But one of them that again it blew me away was in our, and I'll put all these papers up with the podcast episode, but when we're talking about it, you said, okay, I can illuminate this bezel beam generating CGH with a point source, and that gives me approximately or practically infinite bezel beam. And the PSM, great. I have my point source effectively to illuminate it, but I don't have to use that, right? And in the paper, you present a case where you're saying, I have my PSM over here, and my CGH is here, and I can, if I'm aligning some optic, then what's going to happen is I'm going to get the beam, the point from my bezel beam. If I was only aligning it, I should say with the PSM. And I'm going to get, let's say, the reflected light from the surface of my optic. And a problem is that the light that's coming from the CGH is going to be
much less
intense. And so you say, just illuminate it from the backside. Just put something on the other side of the CGH and generate your bezel beam that way and get everything aligned. And then you have a really bright beam from your point from your bezel beam on your detector, and similarly bright point because you can attenuate this light from your PSM that's reflecting off of your optic. Is that accurate or?
Yeah.
Okay.
But I mean, and that's how I was doing it. But I'm more and more going away from that, thinking that you can do it with a single Bezel beam. That you don't have to get to a center of curvature. Because a lot of people say, oh, well, I've got negative lenses and centers of curvature way inside the thing.
Right.
The Bezel beam solves the problem for you.
Right.
You don't have to get
You don't
inside
even need, right.
the lens.
It's a catch-all solution just about.
It seems to be.
Yeah. Let's shift away from strictly optics and kind of ask more general questions, if that's okay with you. So we've described, we talked through how you entered optics, how you came about coming up with the PSM, the applications of it, And interestingly, hopefully for attentive listeners, we also talked a little bit about the idea, kind of, in my opinion, about entrepreneurship of you come up with a fantastic idea and how do you support letting that mature? And you did that in part with consulting. And then we got in the weeds about aligning things with the PSM and with bezel beams. And the bezel beams, anyone that's listening to this needs to seriously download the paper, think about it, find uses for it, because it's really incredible. But I want to get away from that. And when we spoke on the phone prior to this, you had alluded that how you got into optics wasn't that you said at 18 years old, you know what I want to do with my life? I want to enter optics, I want to invent the PSM, come up with alignment mechanisms for bezel beams. And I think that's a deep question. So it's not even a question, but what are your thoughts or insights that you would give to people really at any stage of their career about how to go through their career? What was your takeaway? Because it seems to me that, your career takes you where it takes you. And I'm curious kind of what your thoughts are on that.
Well, I think that so much of our whole life is totally out of our control, right? We didn't choose our parents, for example. We're here, and we've got to make the most of our time here. Mm-hmm. And I think as I said earlier, I think it was a very smart move to be a physicist, or at least my wife said, you can't call yourself a scientist, you're an engineer. But
right.
To have the physics background, because then you're a generalist. There's some fields you can't possibly be a generalist. If you're a heart surgeon, you're a heart surgeon. But
right. I don't want a generalist in that case. But
but it certainly gives you a broad opportunity. I do think that the humanities are important, that you shouldn't go to college as job training.
Right.
Or at least only job training. You really need the humanities to give your life meaning. And in fact, I think of life in general maybe a little bit like putting pieces together in a jigsaw puzzle. Very early in your life, you're putting together edge pieces, and you, throughout your life, fill in pieces, and your life is more rich and rewarding the more pieces you can fill in.
Right.
So, yeah, being a generalist, I was always fascinated when I attended a very nice lecture when I was at Williams by C.P. Snow, who wrote the Two Cultures book, to talk about science and humanities and the cultural difference between how they look at. And in science, things are hard. There's only one, as long as you all agree on the assumptions, there's only one answer.
Right.
If you're a lawyer, you can ring facts around to make them say anything you want to make them say.
Yeah.
So the humanities is kind of fuzzy, which is good. That's certainly got its usefulness. It helps you negotiate. If two people have completely different ideas, you've got to be flexible.
Right.
But physics, law of gravity that's it.
Yeah. Right. There is no fuzziness about it.
Yeah.
I really love that, and I think that it's an area. This is probably the area of one of the areas I'm most passionate about in my life, probably to the chagrin of my girlfriend and my friends. But I think science is deeply fascinating, and I think that obviously there's no better mechanism for saying I observe a phenomenon or some mechanism and I want to repeatably describe it, or empirically be able to describe it. But I think that it leaves a lot out with respect to the fuzziness of life, like you said, insofar as what makes for a fulfilling or satisfying life, or a good life, or why do you do a lot of the things that you do. And it's a pet peeve of mine that so much of college seems to have been, or higher education generally, seems to have shifted more towards this value for just do something that gives you good skills, and kind of away from the humanities. And there's a science fiction book that I really love called Canticle for Leibowitz that touches on this idea, and it paints it in a very extreme way because it was written, I think, during the Cold War. But it paints it between the idea of strictly pursuing science versus they use, monastic monks, and kind of the tension between technological evolution and should we be doing things, or not even should we be, but why? Like, why are you pursuing some things at the expense of not pursuing others? Which is now getting ambiguous, but it just struck me, your statement on the phone even, of you don't know exactly where you're going to go, but I like that sentiment that you should really try to make the most of it. And I particularly like the sentiment, it's worthwhile to pursue the humanities or fields outside strictly of science, just because I think it makes life better and more fulfilling.
Well, the other thing I think is creative people in science, they are just as much an artist as a painter or a sculptor, right? And part of the reason I'm still working is I really enjoy what I'm doing.
Right.
It's just really nice to go home in the evening and say, I made that.
Yeah.
I can see value in what I've done at the end of the day, and
Right.
I'd like to keep adding value if I can. And, my work, I kind of jokingly say I've got a self-funded research lab. I mean, I do plow the money I make from selling PSMs back into exploring.
Yeah.
Another problem that's just, well, the other thing that happens with retirement and working, when you're working, your boss expects you to turn out results, right? And you don't have time to write papers or something you did while you were working. You say, I wonder what would happen if, but I can't explore that now. My boss wants
There's a deadline,
results.
right? There's a deadline for something.
Now that I'm at least retirement age, I can explore all those things that I never got to when I had to earn a living.
Right. Well, do you have any kind of parting advice or words of wisdom for people listening, short of retire and pursue your interest?
Well, I guess, yes, if you ever get fired from a job, look at it as a new beginning. Mm-hmm. Because if you are fired, that's probably you weren't the right job in the first place.
Right.
And that may be the kindest thing anybody ever did to you, was to say, get out of this job and go find what you, because it's sad for people to go to work who are working just because they have to work.
Yeah.
It's so much better that you look forward every morning to going to work because you've got things you want to find out.
It's exciting and you get to,
Yeah.
Well, Bob, thanks so much. My guest again this week has been Bob Parks, and he helped to invent the Point PSM, and he also currently is at Optical Perspectives Group, and we'll link to all of the topics covered today. So thanks so much.
Thank you, Logan.
Yeah.